circuits with craft. In today's video, we're diving into the 2024 past paper and tackling question 1. We'll be exploring the fascinating concepts of positive temperature coefficient and negative temperature coefficient of materials. These properties are crucial for understanding how different materials behave under varying temperatures and are essential for anyone studying or working in the field of electronics. So grab your notes and let's get started. But before we get started, please remember to subscribe to my channel, like if you find this video helpful, and share with your friends. Now, question 1 says that we're to define the following terms in relation to materials. So it asks for a positive temperature coefficient. Now, a positive temperature coefficient refers to a material whose electrical resistance increases as the temperature rises. Now, we're looking at its behavior, and as the material gets hotter, its ability to conduct electricity decreases because its resistance goes up. Now, we can use these, or we can find these applicable in that PTC materials are often used in application where self-regulating properties are desired, such as heating elements, circuit protection, and temperature sensors. So for example, a PTC thermistor can act as a safety device in electrical circuits to prevent overheating. As the temperature rises, the resistance increases, reducing the current and thereby limiting further temperature increase. Now the other one is a negative temperature coefficient. Now this negative temperature coefficient refers to material whose electrical resistance decreases as the temperature rises. In essence, as the material gets hotter, its ability to conduct electricity increases because its resistance goes down. Now, NTC materials are commonly used in temperature sensing and measurement applications, such as in thermistors for temperature monitoring, in electronic devices, automotive sensors, and inrush current limiters. An NTC thermistor is used to measure temperature changes accurately. As the temperature increases, the resistance decreases, and this change can be used to monitor or control the temperature. Now, in essence, materials with a positive temperature coefficient increases in resistance with the rising temperature, while materials with a negative temperature coefficient decreases in resistance as the temperature rises. Now, that was part 1. Now, part 3 says that we're to sketch the resistance versus the temperature to represent the positive and the negative temperature coefficients. So for the positive temperature coefficient, remember that this one refers to material whose electrical resistance increases as the temperature rises. So here we have the resistance increasing on the Y scale and the temperature on the X scale. Now we see here that as the temperature increases, the resistance increases. Right? So as the temperature rises, resistance increases. Now for the negative temperature coefficient, this diagram explains that as the temperature increases, the resistance decreases. So this one refers to the decreasing of the resistance as the temperature increases. So here we find that the temperature is reducing, the resistance is reducing as the temperature is increasing. Remember that the temperature is going from 0, all right? It is rising from 0 upwards. So now question B asks us to state the effect of the flow of current in a conductor. Now there are different things that can happen as current flows in a conductor. Due to the conductor heats up due to the resistance it offers to the flow of electrons. This effect is the basis of many heating devices such as electric heaters and incandescent light bulbs. We could have another effect is a magnetic effect. Now, a magnetic field is generated around the conductor when the current flows through it. This principle is used in electromagnets, transformers, and electric current. Now, note that this question only values 1 mark. So they're not necessarily expecting you to write in details all of these things. All right? And then the last one could be that you have a potential difference in that the voltage drop occurs across the length of the conductor due to its resistance. So the length of one will also affect the flow of current in a conductor, right? So Ohm's law also describes this relationship whereby you will have a voltage drop if there's a change in the current and the resistance. Part B, number 2 of part B, says that it asks you to state the effect of the flow of current in an insulator. Now we know that insulators are material that restrict the flow of electric current. However, if a high enough voltage is applied, the following effects can occur, where you can have what is known as a dielectric breakdown, where the voltage exceeds the dielectric strength of the insulator, and it can cause the material to become conductive, whereby it leads to a breakdown of its insulating properties, and this can result in sparks or arcing. Heating. So although insulators have very high resistance, a small amount of current can still flow, and as a result of this flow, it might cause slight heating, and in extreme cases, it can damage material or cause it to melt. Now, part 3 says that we're to name the most common types of waveform. Now, the 2 most common types of AC or alternating current waveforms generated are sine wave, and this is the most common waveform for AC power. It smoothly oscillates between the positive and the negative values in a sinusoidal pattern. It is used in a power supply and is the standard form of electricity delivered to homes and businesses. The other one is a square wave. Now, this waveform switches abruptly between high and low states, creating a square-shaped pattern, and it is used in digital and switching electronics and for clock signals in digital circuits. Now, part 4 says that we're to state the process of producing a DC voltage from a generator. Now we'll look at the process of producing DC voltage from a generator, and it includes the following steps. Mechanical energy to electrical energy. So this is basically on the premise under which a generator operates, right? So it converts mechanical energy to electrical energy, right? And this is generally done by using a rotating turbine or an engine. Now you have the AC generator, and initially the generator produces what is known as an AC voltage. Now this occurs because the rotating coil within a magnetic field generates an alternating current as it moves. Then it goes through a process of rectification, whereby the AC voltage is then converted to DC voltage using a rectifier, and this rectifier can be made of diodes, which allow current to flow in one direction only, and this converting the AC to pulsating DC. Then you will have the filtering process, where this filtering process is the pulsating DC smoothed out using filtered circuits, typically consisting of capacitors and inductors, and this reduces the ripple and provides a steady DC voltage. Now we have the regulator or regulation, which oftentimes is optional, and this is used to ensure a constant and stable DC output voltage. This is to ensure a constant and stable DC output. Now, voltage regulators may be used to compensate for any variations in the input voltage or load conditions. C of question 1 gives us a table, and it asks us to use the information provided in table 1 and the graph paper on page 7 and plot a graph of the half cycle of the AC waveform with current on the y-axis and time on the x-axis. So in order for us to plot the graph, we need to use the given current and the time values. So we have current values of 0, 7, 14, 23, 56, 68, 76, 65, and 0. And we have some time values in milliseconds: 0, 1, 2, 3, 4, and 5. First thing that we'll want to do is to plot the graph. So based on the numbers that are given, right, so we have 0 to 76, right, and then we have 0 to 5. Good. So we use the numbers given for the current and the numbers given for the time, and this is how we came up with this graph. Now the peak or the maximum value on the graph that you were asked to label on the graph. So the peak or maximum value is identifying the highest current value on the graph. So that's the peak. So that would be the utmost value at the top, or that's the most current value that was given. All right, so that was the highest current value that was given. The mean or the average value, and in order to calculate the average of all the current value, we'll have to use the formula to do so. We'll look at that in a little while. And the root mean square, we'll have to calculate the root mean square value of the waveform as well. Alright, so for the peak or the maximum value, it says that the peak value is the maximum current in the half cycle, and that is 76. And for this, we label this point as the peak value or maximum value on the graph. Right, so here you have it. The mean or average value for one cycle of the AC is 0 due to the symmetry of positive and negative halves. However, if considering only half cycle, you calculate the average of the absolute values of the current. So in order to do that, we'll add all the current values that were given and divide it by the number of current values that we had added. Right, so that would be 0 plus 7 plus 14 plus 23 plus 56 plus 68 plus 76 plus 60 plus 5 plus, well, 0 has no value. And because the 0 is one of the numbers given, we also add them and we divide by 10. When we do that, we get an answer of 30.9. So here we have the mean, which is 30.9. Now the RMS, the value, the RMS is the value for the half cycle, and this can be calculated by finding the IRMS. Right, so the summation of the I squares divided by the total number. Right, or find the root of that. So we would have added, we would square root, or would square all of the numbers that were given for the current, right, and divide it by 10, and then we'll find the root of that. Right, so that was what we did. So 0 square plus 7 square plus 14 square plus 23 square plus 56 square plus 68 square plus 76 square plus 60 square plus 5 square plus 0 square. And then the figure that we'll get for that is 179, 179.3.5, 17935, and then we divide that by 10, and then we'll find the root of that, which is 42.33. So here we have that value as well. And there we have it. So for part A of question 1, it asks you to define the terms as it relates to the positive temperature coefficient and the negative temperature coefficient. And in that, the positive temperature coefficient refers to material whose electrical resistance increases as the temperature rises, while the negative temperature coefficient refers to a material whose electrical resistance decreases as the temperature rises. We also looked at a graph. We were given figures. We looked at the temperature versus resistance graph, right? And we also looked at how current affects, or what effect can current have while it flows in a conductor, right? So we looked at the heating effect, we looked at the magnetic effect, and the potential difference. We also looked at what effect could current flow have on an insulator, and we looked at the dielectric breakdown, which is the breaking down of the material that is used to make the insulation, and what effect does heating have on insulators. We looked at the two main waveforms that are used, which are AC, alternating or sinusoidal waveform or sine wave, and square waves. We also looked at the process that's used in generating or producing DC voltage, and in so you would have the mechanical aspect, where it is converted using mechanical energy to electrical energy, and then you have you need to rectify that AC voltage to a DC voltage, right? And that goes through another set of process. And we also looked at how to plot a graph, right, using values that were given, identifying the root mean square, the peak or the maximum value, and the mean or average. So that's a wrap on today's deep dive into positive temperature coefficient and negative temperature coefficient of materials, straight from the 2024 past paper. I hope this video helped clarify these important concepts and how to apply to real-world electronics. If you found this video useful, please give it a thumbs up, subscribe to Electrifying Circuits with Craft, and hit the notification bell so you never miss an update. Have any questions or topics you'd like me to cover? Drop them in the comments below. Until next time, stay curious and keep electrifying your knowledge. Bye.